So welcome back everyone to this new session of the One Word Probability Seminar. It's a pleasure for me to introduce the two speakers of today, which are Federico and Matteo Quattropani. They will give a tandem talk on quantitative convergence to equilibrium of stochastic exchange models. And the first part will be by Federico Sau from the University of Milan. And so please, Federico, the floor is yours.
Okay, thank you, Luisa, and for the introduction. Thanks everybody for being here, wherever you are. And okay, what I'm gonna speak about today is about a class of interacting particle systems, a specific class which we call stochastic exchange models, at least for this talk. And it's a joint work with Matteo Quattropani, who's gonna present the second part of the talk. And as you will see, the models are essentially the same, and the two topics are a bit, let's say, complementary one to the other for what concerns quantitative convergence to equilibrium. And also Pietro Caputo and Sonu Kim are parts of this work I'm going to present. We are going to present. So just to give like a broad overview of what's going to happen in the next couple of hours, my part of the talk is going to be about relaxation to equilibrium for these stochastic exchange models. By relaxation, think about the spectral gap, which is a very well-known object in statistical physics probability. And I'm going to stick most of the time to a more famous model, the so-called KMP model. And I'm gonna present part of the proof by using a new process introduced by De Masi, Ferrari, Gabrielli, and also generalized by Giardina, Redick, and Fontol, which is called the hidden parameter model. And okay, just to keep in mind, okay, this is about the spectral gap, and our main goal will be to produce spectral gap estimates on general graph. While Matteo's talk takes more a mixing times point of view, is gonna look at a broad class of models with no geometry. And yeah, and this is going to come later. Okay, let's start with this guiding example, the KMP model. And yeah, we need a very few ingredients to introduce it. First of all, we need a graph, an underlying geometry, which for us will be just a connected, undirected, weighted graph. And by weighted here, I mean that we can place symmetric conductances on edges. And these weights are, we call them CXY, and weights on the vertices, which we call alpha of X. Okay. With this underlying geometry, then we will consider models in which we place masses, non-negative masses, on vertices. And we run the following dynamics, Markovian dynamics, which for the KMP is simply select some edges according to some rate, let's say CXY for the edge XY, and simultaneously draw a beta random variable with parameters alpha X, alpha Y. And let me just recall, okay, just to be on the same page, that a beta random variable takes value 0, 1, and has a density proportional to this function here. So the parameters alpha X and alpha Y appear here. And with this fraction, random fraction, let's redistribute the masses sitting on the vertices X and Y in a new way by taking of the total mass on these two vertices, taking a fraction U, drawn according to this beta distribution, and giving this fraction U of the total mass to X and the remaining one. Okay? Just to be completely sure that the model sticks to your mind, let's repeat again with a cartoon. So this is the update that we want to picture. And an equivalent way, which will turn out useful later on, is to say, okay, let's use this U to split some mass first on X and then on Y. In particular, this mass U of eta X will be kept by the vertex X. This mass 1 minus u eta y will be kept by the vertex Y, and the top part will be exchanged. And this is what's gonna happen, producing then this type of update. Okay, and this is the resulting configuration. So the question that we care about is what happens to the KMP in the long run, equilibrium and convergence rates. Of course, okay, the equilibrium situation of the KMP is well known. Okay, I will give a broad overview of the background on the KMP. And when turning to convergence rates, just keep in mind that, okay, I will present things like this, but we always have in mind other exchange dynamics, more general, and this will come in the second part. Okay, I didn't say, of course, if you have any questions, feel free to interrupt anytime or write in the chat, Matteo will answer. So, just a fact, which just to start, is about invariant measures. It's a well-known fact that the KMP admits a family of reversible measures, which are products of gammas with parameters for each site alpha x, and a density, a common average density rho. And for each average density, there is a different reversible measure. But of course, because the dynamics is conservative, these measures are not ergodic. And therefore, it makes sense to, okay, look at the ergodic components of this process. And another remark is that, okay, what the dynamics that we describe, both transitions and rates are independent of the total mass. So essentially, without loss of generality, we can confine our process to just live on the probability simplex, namely total mass equal to 1. This is without loss of generality. And okay, the specific choice is that, okay, we have some names for the conditional reversible measure on this simplex, which is exactly the Dirichlet distribution with parameters alpha, which we denote by dir. Okay, it's a well-known fact that such a distribution, namely conditioning the product measures to be confined to the probability simplex, is a Dirichlet distribution. And here it's essentially the form that this Dirichlet distribution takes. Okay. These are general facts about Dirichlet distributions and products of gammas. They are reversible for the KMP. But what we care about is convergence to equilibrium, which is really this statement here. If we call by L the generator of the KMP on the graph G and parameters alpha and ST the corresponding semigroup, then we have by ergodicity now on the probability simplex that for any initial condition nu, then the process will converge to this unique ergodic measure. And our main task, let's say both of me and Matteo in the two talks, is to quantify this convergence. And there are many ways to do this, mixing times, functional inequalities like Poincaré inequality log Sobolev, and we're going to stick to the Poincaré, the spectral gap. What about the spectral gap? The spectral gap, okay, if you just want to give a very, let's say, general definition of this, is the best constant, the best exponential contraction rate for measuring convergence to equilibrium when applying the semigroup to suitable observable. So it will be the best, the largest lambda for which this inequality holds for any function in the L2 space of our reversible measure, and at least for T large enough. And we would denote by gap G of alpha for the rest of the talk, the spectral gap of the KMP. As long as we speak about the KMP, then if we change model, then okay, I'm gonna speak about it. Okay, very basic facts about the spectral gap. For any ergodic macro process, the spectral gap is positive, so there is exponential convergence to equilibrium. And Another equivalent characterization of the spectral gap, which we must keep in mind, is which holds for, let's say, non-trivial reversible macroprocesses, is the fact that gap coincides with the smallest non-zero eigenvalue of the negative of the generator when viewed as an operator on the L2 space of the associated reversible measure. Okay, so here it's the reason why this exponential contraction rate is really called spectral gap. And equivalently, okay, which we are not going to use, of course, we can also characterize it as an optimization problem over the energies, overall variance one observables, but we're not going to use this for the rest of the talk, so I just leave it suspended like this. What we are interested in is the dependence of the spectral gap on the underlying geometry. And before entering the details of what is known about the spectral gap of these models, let's explain why we call it KMP, where this thing comes from. And okay, let's say the first appearance of this model, actually it's not really the first, because okay, it's as you can imagine, a very simple model, a very general model, which has appeared also before the 82, as we will see. But at least the name that this model takes, KMP, comes from a work by Kipnis, Matteo in the 80s, in which actually they consider not the KMP as I described it earlier, but on a specific geometry, the end segment, with two reservoirs attached to both ends of the segment, and taking just for simplicity, instead of a beta, a uniform type of splitting mechanism, corresponding to the alphas all being equal to 1. And so, okay, this model was then later generalized by several authors. And the main goal of studying this model for Kipnis, Matteo was to understand non-equilibrium steady states, which were generated by placing the two reservoirs densities at two different values, okay? Therefore, creating currents and creating non-trivial non-equilibrium correlation, long-range correlation. Okay, so this is where the KMP name comes from. If we focus a bit more on the problem of convergence to equilibrium, then recently, again on the segment, Caputo, Labella, Coin, in 2020, by calling it in a different way, adjacent work on the simplex, they studied, in the case of beta splitting mechanism with alphas all being constant and larger or equal than 1, they studied the mixing time, and they established also a result on the spectral gap, as I will explain just in the next slide. But actually, this model has a much older, let's say, ancestor, which is the Cox-Walk, where the Cox-Walk is a model proposed by Katz in the 50s as a mean field model of randomly colliding particles to really try to derive from that Boltzmann equation from kinetic theory. And yeah, it's a mean field model, so if particles are represented by vertices, it means that we are working on the complete graph. And it's not really the Cox-Walk, because the Cox-Walk really looks at the momenta of particles, which are exchanged at random. But if you look at the energies, so the squares of the momenta, then these energies are really, again, a KMP model on the complete graph with a certain choice of weights alphas equal to 1 alpha. Because here the redistribution rules, let's say, the scattering rule for the momenta is chosen to be a uniform between 0 and 2 pi. Okay, these facts are well known to the community, and yeah, the problem of determining the spectral gap of the KMP model or Cox-Walk comes really from the original work of Katz, in which he proposed to establish for a suitable normalization of the rates at which particles collide. So by taking this normalization 1 over n, where n is the size of the graph, he asked really if the spectral gap of this n particle system was uniformly bounded away from 0, ascending the number of particles to infinity. And this was for the same reason as we want to study it, in a sense to quantify convergence to equilibrium for this particle system and try to transfer this information to the limiting Boltzmann. After many years from Katz's question, this question was answered in an affirmative way. First by Elie Jean-Fraisse, which proves the claim that Katz's question asked for. And then almost simultaneously, and a few years later, Carl and Carvalho-Loss, and also Caputo with slightly different techniques, determine the spectral gap really its exact value, okay, which is this number here. There's no need to remember it for the rest of the talk, but it was discovered in a much more general form than from the model proposed by Katz. It's true for any choice of alphas equal alpha constant and positive. And this is on the complete graph. Again, I stress. And what's interesting is that this spectral gap was really realized. So the worst exponential contraction rate to equilibrium was attained by quadratic type of observables, exactly of this form. It is something that we're gonna encounter also later. As I said, okay, there is also a second work in which the spectral gap of the KMP has been determined. Again, its exact value, 1 minus cos pi over n on the n segment by Caputo, Labella, Quan, in the regime in which, again, alphas are all constant and larger or equal than 1. And in this case, what's interesting is that this time quadratic statistics are not the worst ones, but linear are the worst ones. And there is also an explicit expression for this type of statistics. And then let me just remark that more recently, Labbe Petit also studied still on the segment, but a slightly weakly, let's say, asymmetric version of that. And they also established some similar results to this paper concerning spectral gap and the mixing time. So just to wrap up on the complete graph and on the n segment, as you can imagine, there are many symmetries, and this allows us to even get explicit values for the spectral gap of the KMP. If you are on general graph, no hope for explicit values, but yes, there is some hope for reduction. Namely, saying, the spectral gap, of course, it's a worst case over all possible statistics of our process, but is this exponential contraction rate captured well by some finite dimensional space of statistics or some low degree type of statistics like linear or quadratic? And this is what we're gonna try to attack in this talk. And it's captured by this main result, by this box, in which we show that for all graphs and all weights, in general, the spectral gap of the KMP, of course, is captured above by it's at least the worst case exponential contraction rate of linear statistics, but it's actually controlled also below by that, up to paying a cost, which is this factor gap. So here I wrote it a bit more explicitly in words. This gap 1 really corresponds to this worst case linear statistics, and this factor here is completely explicit. And essentially depends only on alpha. Okay, here there is a mean over just the edges, so we can just take the mean over edges, but in principle we can take a worst bound, taking the mean over all unordered pairs, and we get something which is independent of the graph. Okay, as I said earlier, the upper bound is surely not surprising. What is the main result is really the lower bound. And then a second remark is that, okay, this factor here, unfortunately, is always between 0 and 1, never 1. But it's very, very explicit. So in particular, if we take just alphas to be constant, then we get really just a number. And by taking limits, we also get, actually, by sending alpha to infinity, we get 1. And by sending alpha to 0, we get another number, which also has a meaning, but okay, I will not spend too much time on that. And let me just remark that, okay, taking alpha to infinity really corresponds to the fact that the betas, by sending both parameters to infinity simultaneously, will just converge to a Dirac in 1/2. And also the KMP in this limit will converge to, instead of doing a random redistribution, we'll do a deterministic redistribution at some random times. And this way we recover the Aldous average. Okay. And this type of estimate is completely coherent for what is known about the Aldous averaging. And let me say that these two bounds, the blue and the green one, are both sharp because of the examples I told you before. So the upper bound is sharp because it's matched on the end segment, and the lower bound is also sharp because it's matched on the complete graph. Okay, this is just, if you see here, this type of expression is very, very similar to the one I showed you before on the complete graph. And this gap 1 in the specific case of the complete graph is just 1/2. So it's really exactly the same. So if we want a better bound on general graph, we cannot do that. So before introducing other models, I try to explain the strategy of the proof of these very, let's say, of these two inequalities, actually only of the important one, because the first one, it's kind of trivial. And I want to explain just for the KMP, and later we will see how it easily generalizes to more processes. And let me just remark that the strategy that we use has to differ a lot from what has been applied so far for the two known cases. The complete graph, first of all, in all this works essentially. The starting point is Liu-Yao's martingale method, which somehow is based on some conditioning and an induction argument on the size of the graph. And this is possible, and this is very effective, allowing to get explicit values of the spectral gap because of the symmetry of the complete graph. Okay. While on the N segment, the arguments by Caputo, Abel, Lacoin employ something very, very specific of the and very powerful of the N segment, which is a stochastic ordering that can be implemented by a ground coupling, essentially, of the corresponding height function of the KMP energies. And also by using this stochastic ordering plus some positive association, which comes from the fact that the alpha are taken to be all larger or equal than 1, then it's possible to get a very sharp bound on the spectral gap. On a general graph, which is our setting, we cannot really follow this approach. Neither of them, if we want to really have sharp bounds. But we use something much more elementary, which is, can be traced back to, these works of Mu-Fa Chen and Fengyu Wang. But as you will see, I mean, the argument is very, very general and probably known even before. But the twist is that we are not going to apply this method directly to the KMP, but to its hidden parameter model. And this is, let's say, this is what makes the strategy that we use very, very simple again. I hope you appreciate it. So the starting point, it's really just a remark, that we need to speak about, we are interested in spectral gap, we need to speak about eigenvalues, and polynomials will play an essential role. So let me just write here, just for convenience, the generator of the KMP. As you see here, there are just updates which occur at a rate which is just proportional to the conductances of the edge xy. And then there is a redistribution, which is done according to a certain operation, the linear operation, which is really just the KMP updates written in this fancy form, according to a random U distributed as a beta. Okay, and from this expression of the infinitesimal generator, I wrote it here because from this expression, you should be immediately convinced that if we take a polynomial of degree at most k in the eta variables, which has in general this form, then the generator leaves this space of polynomials invariant, maps a polynomial of degree at most k again in a polynomial of degree most k. This is because this type of linear redistribution doesn't change the order, the degree of the polynomial that we started from, and also the rates do not depend directly on the etas. So we are not gonna destroy the polynomial form and also the degree. Okay, so this is our basic starting point, which comes with many important consequences that we're going to exploit fully. First of all, okay, we can really just restrict, if we want to look for eigenvalues and eigenfunctions, just the action of the generator on these subspaces, finite dimensional subspaces, and find polynomial eigenfunctions and polynomial eigenvalues. We can call it like this. Moreover, because the reversible measure is really a nice Dirichlet distribution with non-vanishing parameters, L is well defined and self-adjoint because of the reversibility on the corresponding L2 space. And this allows us to apply the spectral theorem for self-adjoint operators. And therefore, the L2 spectrum will really be pure point and will coincide with all polynomial eigenvalues. Okay, so we are in good shape in order to set our analysis, and we are going to look for gap just by restricting, let's say, the finding of bounds for spectral gap just by looking at the smallest non-zero eigenvalue of L, but restricted to just these polynomial dimensional subspaces of polynomials of degree k. Okay, so this is just preliminary. And we're going to start a bit with try to explain the general method. So take a candidate polynomial eigenfunction with eigenvalue, positive eigenvalue 0, lambda, strictly positive, and with being a polynomial of degree at most k. Then it's a matter of fact that the mean of this eigenfunction must be 0 when we compute the mean with respect to the reversible measure. And then the following chain of identities and inequalities is obvious. The first one is just a straightforward consequence of the definition of being an eigenfunction. The second one just uses the fact that the eigenfunction has mean 0 and mu is invariant with the semigroup. And here is just a sharp upper bound. Okay. And then the goal becomes to find some suitable constants, C and rho, independent of the time, such that this right-hand side is bounded by a constant C, e to the minus rho. And if we manage to find such constants, taking the logs on both sides, and just remark that here, in order to take the log, we really need this to be a non-trivial thing. So find the configuration for which f gives a non-zero value, and then after taking a log sending t to infinity, we immediately get the lower bound of lambda in terms of this rho that we find. Okay, this is elementary. So how to prove this bound? What Chen and Wang propose is to prove this bound goes through two main steps. First, find a control function for f. By control function, we mean just a function defined on omega omega to be bounded, such that essentially f is Lipschitz with respect to this control function. Lipschitz, you understand what I mean here. This control function is not necessarily a distance, but okay. And then find the Markovian coupling of two copies of the process for which, for this control function, we can prove an explicit contraction. exponential contraction with some rho. And by putting together these two things, we would obtain, because the control function is bounded, we would obtain this. Okay. And let me just remark that this type of strategy, if D is a distance, it's really okay. The first part is really the eigenfunction is Lipschitz with respect to this distance, and the best rho that we find in the second point is just the curvature with respect to this distance, the Wasserstein-1 curvature of the symmetry. Okay, at least gives us a bound for this curvature. But in general, okay, this D will not be a distance, but okay, this is a slightly more general set. Okay, let's try to see.
Sorry,
why...
can I interrupt you one
Of
second?
course.
So it's not a distance, but you just need it to be bounded, and so.
Yeah, bounded. Of course, I mean this condition here implies that it must be 0 on the diagonal. Otherwise, this thing will explode, and this is the only requirement that you need. In practice, it will be a distance or a power of a distance, because I mean this is what's easy to establish. I mean, what makes this thing a bit easier to analyze.
Okay, thank you.
Yeah. So this is a very, let's say, broad strategy, and but it can be applied already on the two examples of the complete graph and the n segment, which I presented so far. And this actually has been done by Maxime Auré around 10 years ago now. And let's see what it gives for some suitable choices of control function and coupling. So in his paper, he takes as a control function the square the Euclidean distance, so the Euclidean distance squared. So it's the square of a distance. Okay, I repeat myself. And there's a coupling, the very normal one, the very standard one, the grand coupling, in which if we have two configurations which we want to couple of the KMP, we couple them by simultaneously updating the same edges by using the same random fractions U. Okay, and this will create, of course, a coupling. It's called grandpa coupling because we are using the same alley. And what's nice to see, and also not difficult to see, is that, okay, if in order to prove an exponential contraction rate, if we take really just how these, let's say, control function contracts infinitesimally over time, we get an explicit expression with two main terms. And the nice thing is that on the complete graph, both lines, because we are on the complete graph, are really proportional to the control function that we started from, with a negative factor in front. And this is exactly what we need after applying Grombol's inequality to really get an exponential contraction rate. And the crucial remark is that this second line is, in order to be written somehow linked to this square distance, really crucially use the fact that we are on the complete graph, because when we are on the complete graph, the summation just over y fixing x of this term exactly here, because c is constant, is really just equal to 1 the conductance at eta x minus eta x prime, because both configurations have mass 1. Okay, actually, this strategy has been applied also on the n segment. Of course, I mean, as this last term on general graphs, if we're not in a mean field situation, it's not really clear how to deal with that. But on the n segment, again, the strategy has been used by Grigor, Kani, and Zas by taking again the grand coupling and taking again the square Euclidean distance, but not between the two configurations, but there. And actually, okay, I don't write here the computations, but by choosing the height functions and try to couple just the height functions and computing the square Euclidean distance between them, they also get they can manage somehow to prove an infinitesimal inequality as the one in the previous page on the end set. However, okay, as you see, so if you want to apply the same strategy on general graphs, we don't have height functions, we don't have this nice trick by summing up over all edges. So either we need to change the distances as Grigon can us do, or change the coupling. But okay, we don't do this because okay, we found likely an alternative. We just use a different process, as I anticipated earlier. We use the so-called hidden parameter model, which was introduced around now 1.5 years ago by De Masi, Gabrielli, and Ferrari. Ferrari and Gabrielli, okay, here written in the wrong order. So what is this KMP's hidden parameter model? It's a different model in principle, which lives on a different configuration space. So again, we imagine to have masses between 0 and 1 all distributed on the vertices of the graph. And the dynamics is kind of very, very similar. So we, on a general graph, we follow essentially the same randomness of the KMP model. So we update edges according to the conductances, CXY if the edge is XY, and we use the same uniform, the same beta distribution to do the updates, but the update rule is slightly different. And here I tried to put it one on top of the other just to see the differences. And the difference is here, just in these two terms. Okay, 1 minus u theta y instead of u, and u instead of 1 minus u. Okay. And then the question is, okay, why should this thing be related to the KMP? Okay, it's very similar, so maybe there is a relation between the two, but okay, if we just want to remember it also after this talk is finished, just keep in mind that, okay, if we want to write down an update for the KMP as a vectors and matrix product, we can do this by using the same matrix. We can view the KMP configuration as a row vector, while the hidden parameter model is the column vector. And we are multiplying from the right and from the left. HPM from the right and KMP from the left. And this is the only difference. And in a sense, okay, if we want to use the same randomness, somehow, okay, the KMP will correspond to keep on multiplying these type of matrices that you see here, okay, which will be related somehow to, okay, we need to decide which edges we are updating and which U to choose. But once we choose this, we can really just generate a configuration of the KMP in this way. And in a similar fashion, we can do the same for the HPM, for the hidden parameter model, just by reverting time. So in this sense, if we imagine that the KMP is evolving forward in time, the HPM is evolving backward. Okay. Okay. From this point of view, we want to use these hidden parameter models to prove some convergence rates to equilibrium. So we need to understand at least a bit better what's the long run behavior of this hidden parameter model. And a very simple statement without going into the main properties of this model is that, okay, the matrices that we use for the updates are stochastic, and the hidden parameter models are for us the column vectors. Therefore, it's clear if you have a stochastic matrix multiplied by a column vector that if we start from a column vector which is constant, this will remain exactly constant again, and it's going to be actually exactly the same. So in terms of processes, this means that if we start from a constant configuration of the hidden parameter model, this is an invariant configuration. Okay. And more generally, if we start from anything else, in the long run, since we are in a connected graph, as t goes to infinity, the the hidden parameter model will converge just to a flat configuration in which the height is possibly random, but it's going to be flat. And therefore, the nice thing of this is, okay, one will say, okay, why do we go now to some process which has so degenerate or singular invariant configurations or invariant states? Well, okay, in terms of trying to understand some quantitative convergence rates to equilibrium for these models, it's much simpler because in order to, we don't need to do any coupling, but we only need to control the spatial fluctuations of the hidden parameter model because they will die out. And we can actually quantify this in a very simple way. And trust me that, okay, a way to do this is to really look spatial fluctuations of a functions are really captured by its variance with respect to what? To, okay, one needs to be, let's say, careful about which kind of invariant measure we want to do. We want to measure spatial fluctuation, but trust me that this is the correct one. And for this observable, we can prove explicit contraction rates with a constant rho, with a rate rho, which is this factor here, which is precisely the lower bound that I wrote in the main result. So this gamma, this factor gamma, times the worst case spectral gap for linear statistics for the KMP. Okay, and this is a computation. I'm not gonna present it. It's not very interesting because it's very straightforward. And so, as I said already, this rho that we get here is really the lower bound that we get for our main result. And this variance is the control function. And note that we do not need any coupling because we are just looking at spatial fluctuations of the hidden parameter model. Okay, now the last step that we are missing is how to connect this contraction rate that we obtained for the hidden parameter model to the one of the KMP. And this is these final slides. So this is I'm gonna go a bit through how to perform this step. Okay, remember that we start from an eigenfunction, polynomial eigenfunction with some eigenvalue lambda. This is exactly where we left before entering into the parameter model's details. And as a matter of fact, okay, this polynomial has some coefficients psi, and if you write it this way, then it's simple to see that the action of the generator of the KMP on this polynomial translates into an action of another operator on the coefficient. And this generator will be, okay, I will not enter into details, will be the generator of a k-particle system associated to the KMP. And what's important to see is that, okay, since this mapping of passing from coefficients to polynomials is one-to-one, then this will also imply that also the coefficients satisfy a certain eigenvalue equation with the same eigenvalue. And with this generator of a k-particle system as an operator. Therefore, if we have an eigenfunction for the KMP, we get an eigenfunction for this k-particle system. We can use now this eigenfunction to construct another polynomial, now in the theta variables, not in the eta variables, by writing down this polynomial, which is exactly the same as the one in the previous slide, except for an additional coefficient here, which I'm not going to spend too much time, but okay, it has a formula, but it's related to the reversible measure of the associated k-particle system. This is what I just said. And okay, again, as a matter of fact, the nice thing is that, okay, the action of the k-particle system generator on the coefficients, when lifted to these theta variable polynomials, translates into an action now with a different operator on the polynomial itself, on the theta variables. And this new action is really the hidden parameter models generator. And we call this type of relation a backward intertwining relation because it involves the hidden parameter model. And what's nice to see also by linearity is the fact that if we start from something which is an eigenfunction for the k-particle system, we also obtain an eigenfunction for the hidden parameter model with the same eigenvalue. And so to recap, we started from a polynomial eigenfunction for the KMP, and by writing it down this way, we obtain an eigenfunction for the HPM, for the hidden parameter model. Okay, and now the last step is to say, okay, how to make sure that this eigenfunction really can be controlled by in a nice way, and it produces then an exponential contraction rate which allows us to bound from below this lambda. We need to assume something on the eigenfunction. Namely, we need to assume that it's a really polynomial eigenfunction of degree not smaller than not strictly smaller than 2. So it must be really a polynomial eigenfunction of degree at least 2. And this is the only thing that we need, because, okay, if we have this assumption, then, okay, it's not difficult to see that this polynomial here, it's also equivalently written by adding here some arbitrary constant, okay? And this is really uses this property in an essential way. In particular, since we can place any constant, we can also put the constant that it's the mean of the theta. Okay, it's not a constant anymore because it depends on theta, but it's a constant which does not depend on space, so it does not affect the definition of G. And by placing this choice of the constant here, we really get just by Cauchy-Schwarz an upper bound, which is in terms of the variance. And now, since we have an exponential contraction rate for the variance of theta, we are in business, and the proof is concluded. Okay. Now, in the last minutes, I will go through some generalization very quickly. Just let me say that, okay, I presented everything for the KMP, but what's been really essential so far is the invariance of the space of polynomials and the fact that we have polynomial eigenvalues, and the Markovianity of the hidden parameter models, and the fact that we could compute for, just by having the transition rates, we could compute an explicit exponential contraction rate. These two properties, these two main properties, are actually something that you can find in a variety of models, which are all, let's say, summarized here, which is exactly the same picture as before, but in which, okay, for the site X, we are splitting according to a certain random variable U. But for the site Y, we are choosing another random variable V. And there can be a relation between these U and V. But the most important thing is that these three properties are satisfied, namely that the rates at which these splittings occurs are independent of the configuration eta. The update is linear and is conservative. Conservative in order to have such a very degenerate, if you want, hidden parameter model, okay, which converges to flat configuration. And then once you have these ingredients, you can write down the most general stochastic exchange model that you want in this form for some rates given by this measure beta xy du dv, which allows us to choose the values of these two random variables in V, and then the rates are the updates are encoded in these matrices.
Fede, sorry, my connection is not very good, so maybe you said it. So U and V, so they don't need to be independent, or so.
Yeah, exactly. So in the next slide, I will say that you can impose further conditions on U and V, but in principle, you just need this type of condition. So U and V are some random variable. I hear there is a typo, sorry, there should be a V.
Okay.
Yeah, but the rates at which, let's say, the values that this U and V must take, the rates of these.
Also, because now I'm thinking in the other model, U and V is equal to U. They're definitely not independent.
Yeah. So it's exactly here. So I take the occasion to fit to this thing. So if you want to look at the KMP, U is the beta alpha x alpha y, and V is defined deterministically as u minus v, 1 minus v. Okay, so I anticipated your question. But also, okay, there are more models which can be considered. For instance, if one takes v identically equal to 1, so always when we choose x and y in this order, never updating y, never moving the mass from y, but only from x to y. This is exactly what this model does with some certain rates. And another one is in which u and v are independent and are both beta. And here we need to introduce maybe another parameter, okay, this kappa. And okay, the fact that they are beta is really encoded in this way. Okay. And it's a matter of fact, I presented these three models because it's by direct computation, it's possible to verify that all these models are reversible with respect to the same Dirichlet distributions of parameter alpha. Okay. And the main result that we can get is general upper and lower bounds for the spectral gap of all these models in terms of just linear statistics with a kind of explicit gamma. Okay, I'm not writing it here because, okay, it's a bit long if you want to write in full generality, but what's interesting is that this factor gamma, which was always between 0 and 1 for the KMP, actually can accommodate, depending on how we choose the rates, can accommodate also situations in which it is larger or equal than 1. And just keeping in mind, okay, here, okay, there is a typo here. I should have put in like gamma L mean 1, because of course, if gamma L is larger or equal than 1, then this inequality is of course false. But we just need this gamma L larger or equal than 1 in order to have a full identity. So this would mean having this condition, which is, this is a sufficient condition for this gamma L greater than or equal than 1. It's a sufficient condition to have a spectral gap identity for this stochastic exchange. And actually what's nice to verify is that for the two models I presented before, it's thanks to this criterion, it's immediate to check that there are situations, non-trivial situations for which this condition is verified. Actually, when alpha mean is larger or equal than 1, alpha mean is larger or equal than 1 plus 2 kappa. Kappa was the extra parameter of this immediate exchange model. And let me just say that also this lower bound is always saturated. Okay, of course, gap 1 is always saturated when we have this condition. And this lower bound is always saturated on the complete graph when the alphas are all constant for both models. Okay, so what's more into now, my time is over. Just let me, okay, just really very quickly just say that, okay, also what we get through this analysis is a sufficient condition for the existing uniqueness of an invariant measure for all these models. And also, actually, our techniques, okay, we focused on the reversible case, but actually lower bounds for eigenvalues are always true. Actually, what we get is lower bounds for the eigenvalues of all the K particle systems which were appearing in the proof. And this is especially meaningful when the update rule is singular, degenerate, for instance, for averaging models, for which there is no sensible notion of let's say, non-degenerate reversible measure, but also when the system is non-reversible. Let me say just, okay, it's well known, so we do not discuss really much open systems in contact with reservoirs, but essentially if it's a general fact that linear statistics for these open systems, when the reservoirs interact, are suitably chosen to mimic the bulk dynamics, linear statistics are always the worst case. And more to be said on stochastic exchange models in the next talk. And let me thank you for that.
Thank you very much. Thank you very much for your talk. And I guess we are a bit strict on time, so maybe there time for a couple of quick questions. Are there questions? So please just unmute yourself or raise hands or write in the chat, whatever. Let's see. We will probably have time also after Matteo's talk as well. But let's see. So
maybe just one quick question.
yes, please.
If I understand your studio correctly, this is based on some construction of a geometric simplex where then you come to the Dirichlet distributions. How do this simplex construction comes in, and could anything different also be included instead of simplex and instead of Dirichlet distributions in the analysis? Thanks.
Yeah, thanks for the question. So, okay, so the fact that we choose the simplex, since we need to assume anyway the fact that in order to have a result, we need to assume that the rates do not depend on the configuration, somehow sort of linearity of these models. The fact of restricting to the simplex or not is not really, it's a bit arbitrary, it's without laws of generality. What's maybe more important to say is the fact, okay, I always spoke about the Dirichlet type of distributions. Of course, the Dirichlet distributions arise naturally when conditioning a reversible product measure to be confined on the simplex. But actually, our lower bounds for the general models hold also for any other reversible measure supported on the simplex. And let's say non-trivial lower bounds for the spectrum of the generator are obtained anytime the reversible measure is absolutely continuous with respect to the uniform measure on the simplex. So, of course, there are many absolutely continuous measures supported on the simplex. And yeah, our lower bound strategy works also in this case. For more singular measures, of course, there's no sensible notion of L2 space, so we only have bounds on eigenvalues.
Okay, thank you.
Thank you.
Thank you. Are there other questions? So maybe I just end with some, but I mean, I'll repeat myself again. So you said that you basically can adapt the strategy if you have a more general rule for these updates.
Mm-hmm.
And this is based as well in this like hidden parameter model as well.
Absolutely, yes, yeah. Because let me go back very quickly. I mean, yeah, up to the typo, there should be a v. So this is stochastic metrics, and okay, if you agree that the hidden parameter model is the column vector, let's say, of while the original process is the row vector, then it's sufficient to have a stochastic matrix to have a hidden parameter model of this type, and the contraction rates. I mean, using the variance is always a good idea to prove to have an exponentially contracting coupling, and we'll give you a different constant, but it's effective.
Okay. Yeah. Okay. Thank you very much. And
thank you.
I think we can thank you again, and maybe let's take a couple of minutes as a break, and then Matteo can prepare his slides, and then, so let's say that we start back in 2-3 minutes. Thank you. So let's thank Matteo Quattropani for being here, and let's start with the second part of this talk. So please, Matteo.
All right, so good afternoon, everyone. And would like to start by saying thanks once again to the organizers of this seminar series for the opportunity to present here our research. So as anticipated by Federico, on this talk, I will stick to the sort of models he already introduced, but from quite different perspective, again, concerning quantitative convergence to equilibrium. So let me be slightly more precise on this. So the focus of Federico's talk was really on the relaxation of equilibrium of these exchange models. Think about the paradigmatic example of the KMP he used throughout the talk. So his approach was more functional analytic, trying to compare the spectral gap of the generator of the whole exchange model with the spectral gap of the same generator when it's confined to acts on linear functions. And the real novelty of this approach was on the generality of the graph underlying the dynamics. While in this talk, rather than relaxation time, I will adopt more a mixing time point of view. Namely, I will introduce some metrics that I will then adopt to measure the distance to equilibrium of our process. And for a given threshold, I'm interested in studying the time that the process needs to be near to equilibrium within the threshold that I fixed. So it's really in the spirit of Markov chain mixing times. But contrary to Federico's talk, here we will have no geometry. Namely, for most of the talks, the models that I will be interested in are of mean field nature. Namely, every vertex interacts with every other vertex, or the graph is the complete one. And of course, if as Federico pointed out, this non-geometrical setup is not interesting for the KMP in the sense that it was already known how to compute the spectral gap in that setup. While here, I mean, something interesting can be obtained even in this simple geometric setting. So to explain our motivation in performing this analysis, let me introduce what is arguably the simplest stochastic exchange model you may think of. Despite this simplicity comes at the cost of some degeneracy, as I will now explain. So let me consider the following setup. I'm on the complete graphs, so I will adopt some sort of kinetic vocabulary for which what Federico called the vertices of the graph, I will now call them the particles of my system. So I have a collection of n labeled particles, which are those represented here in blue. And at time zero, my system will be equipped with a certain amount of energy attached to each of the particle. And I will denote by eta zero in the same notation that Federico used before, the energy configuration of my system. This model will be conservative, so makes sense to stick to the simplex as Federico did. Actually, I used this simple capital delta while Federico used an omega, but it's the same simplex. That is conveniently identified with the set of probability distributions over the set of my n labeled particles. And then I consider the following discrete time dynamics. And in fact, another difference compared to Federico's talk is that here I will only consider discrete time stochastic processes. This is just to ease the exposition, and in fact, everything that I'm gonna say will go through also in the case of continuous time up to some renormalization, of course. So my dynamics will be on the simplex. At time zero, my system will start with this prescribed initial configuration, deterministic, and then at each discrete time, I select two distinct particles at random, say X and Y, and then I do essentially what Federico already did. So I split the energies associated to these two particles, but not accordingly to any random variable, just deterministically in two halves, and say that each particle exchanged the top half with the other particle, like this. So the only randomness involved in the updates is just on the choice of the particles that are going to perform the update. And there is no random variable U for the moment. Of course, after an update, the energies of the two particles equalize. And I keep doing this, and it's intuitively clear, at least, that as time goes by, eventually this system will converge to a degenerate steady state in which all the particles have the same configuration. Since we are on the simplex, the energy at each particle will be given simply by 1 divided by the number of particles. Well, so this is the degeneracy I talked about. So there is no nice steady state like the Dirichlet one that Federico talked about for the KMP. Here, the steady state is simply the Dirac on this specific point on the simplex. But on the other hand, if we want to understand the way in which this system converges to equilibrium, then we can do something in the spirit of the HPM model I did before. Namely, we can exploit the singularity to study the convergence to equilibrium using some sort of empirical measure. So the idea is that eventually the configuration will randomly approach the center of the simplex. So let me take my favorite distance on Rn, say the L1, and compute at time t, which is the distance of the current configuration and the center of the simplex. Of course, if at the beginning the configuration eta 0 charges all the energy on a few particles, and we are interested in the thermodynamic regime in which n is very large, well, then at the beginning this quantity here will be roughly 2, and then as time goes by, it will approach 0. So, very naive question is, how fast does the convergence to 0 of this sequence occur? Well, let me point out that being this an empirical distance, well, this is actually a random sequence. So it depends on the updates, on the sequence of updates that have been performed. Nevertheless, it's easy to be convinced that this random sequence is almost surely non-increasing. And therefore, the question about the decay of this sequence actually makes sense. Well, this model is pretty simple and natural, and as you can imagine, appear here and there in the literature, especially in the computer science literature, where this model is used like a toy model for opinion dynamics. But I won't talk about the related literature inside the computer science community, but rather tell you the story of this model within our community. So the question in the previous slide, the one about the rate of convergence of these simple dynamics, has been asked by Jean Bourgain to Percy Diaconis in the early 80s. So this question seems quite innocent looking, but nevertheless it remained answered for quite a while. Around 2012, David Aldous and Daniel Lanoux introduced the network version of this model, which is more in the spirit of what Federico just presented, namely particles are organized as vertices of a network. This network may have conductances, and then you study this model in continuous time. In this paper, the authors introduced some soft but rather general ideas that can be used to control the convergence to equilibrium of this stochastic dynamics. But a precise answer to the Bourgain question arrived only a few years ago in a paper authored by Diaconis himself, together with Chatterjee, Sly, and Zhang, in which they provide a very refined answer to the question about the convergence of the empirical L1 distance. So what is interesting is that this paper somehow triggered a revival of this model. And suddenly, in the coming years, several people start working on it from this different perspective, not just mixing times. But somehow, this paper raised the attention of this model, on this model once again. So the very natural next slide here is about the answer to the Bourgain question by these four authors. But before going to that, let me do a small detour mentioning the so-called cutoff phenomenon. So cutoff phenomena is something that it's not topic in discrete probability, at least in the study of finite Markov chains. For those of you who are not familiar with mixing time, just let me explain what this is about. So you consider a sequence of ergodic Markov chain on a growing state space. So for every n, you have an ergodic Markov chain on n states. And I will call pi the stationary distribution of this Markov chain. Then one is typically interested in studying the convergence to equilibrium of this Markov chain by looking at the deterministic sequence given by the total variation distance at time t, well, from the worst case initial state. Namely, you look at 1/2 of the L1 distance between the t step of the evolution of your chain started at state x and the steady state evaluated at the same point. Well, this time, this is a proper deterministic sequence, and you may wonder how this look like in the limit of n going to infinity. Well, of course, since the state space is growing, if you want to appreciate some non-trivial behavior of this sequence, you have to rescale time properly according to some function of n that depends on the model. So let me rescale time on this, what I will call the mixing time scale. Well, in this setup, the cutoff phenomenon is simply an abrupt convergence to equilibrium on the mixing time scale. What do I mean? Well, in the limit as n goes to infinity, you can identify precise constant on the mixing time scale, t star, say, such that if you take a time t, such that in the limit as n goes to infinity, the ratio t divided by t star is smaller than 1, then your system will be arbitrarily far from equilibrium in total variation, while if this ratio is in the large n limit larger than 1, then you will be arbitrarily near. So this sort of phenomenon has been observed for the first time in the 80s in the pioneering works of Diaconis and Shashani and Aldous and Diaconis in the context of car shuffling. And since that moment on, the community worked quite a bit on this phenomenon that you can read somehow as some sort of dynamical phase transition. Typically, these sort of results are accompanied by some refinements, namely by the identification of a smaller time scale compared to the mixing one, which is typically called the window or the cutoff window, such that if you zoom in around the cutoff point by this window, then you can actually see that your sequence converges toward a smooth profile. This is usually called, in fact, the cutoff profile. Well, in the context of finite Markov chain, in the last few years, several breakthroughs have been registered. Nevertheless, it is important to point out that a complete picture is still missing. So the subject is still alive. We have some very general necessary condition for cutoff. We have also some sufficient condition when you confine the Markov chain that you study to be in some class. You have some equivalence of this phenomenon to other phenomena. But still, I mean, a theory that encompasses all the possible instances is still lacking. And if you go to the setup of continuous state space Markov chain, like the redistribution model that Federico talked about, well, there the situation is even less developed. All right, so for those of you who are not familiar with mixing times and cutoff, there is a naive parallel that one can take in mind between this dynamical phase transition and a much simpler and well understood concentration phenomenon for the sum of IID random variables. So take a sequence of IID random variables, say non-negative, with proper moment conditions, and call Sn the cumulative sum of the first n element on this series. then you know that by the weak law of large number, if you look at the tail probability of this Sn, as n grows, if you rescale this t by n, then you will see exactly the same picture of a cutoff, where the cutoff point is simply given by mu, the expectation times the number of random variable that you are adding. And moreover, if you zoom in around this cutoff point by a window of order square root of n, then by the CLT, you know that this function here, in this after the rescaling, converges to a Gaussian tail. So this parallel might look quite naive, but despite this, the picture is exactly the same. And I would like you to ask you to keep this parallel in mind, since I will be back to it by the end of the talk. So we are now shaped to present the result by Chatterjee, Diaconis, Sly, and Zhang. So what they do, well, they identify two quantities that not by chance I named T star and TW. One is of order n log n, the second one is much smaller, of order n square root log n, with two explicit constants in front, such that if the initial configuration of your averaging process charges all the energy at a single particle, then if you take any constant beta, a real number, and you look at the empirical L1 distance of the configuration at a time T star plus beta TW, well, this random variable converges in probability to twice a Gaussian tail, evaluated at minus beta. So this is exactly the same picture. Of course, this is now a random sequence, so this converges in probability. But if you prefer, just put an expectation here in front and just weaken this result a little bit, and you have exactly the same picture. So there is a cutoff at time n log n with a window of order n square root log n, and inside this window we have this nice Gaussian profile. So if you stick to the spirit of the previous talk, in which Federico tried to compare the gap of the generator of exchange model to the gap of that generator when it's constrained to act only on linear function, well, the natural analog of that approach in this setup would be comparing the mixing time in this empirical sense of the averaging process with that of a single random walk on the same graph. But in this case, the situation is much less scattered, and there are instances of graph for which the two behaviors are pretty much the same, and others for which they are not. And there are still a bunch of open problems in this respect. So this is the only slide in which geometry matters in this talk. And it's just to say that even for this very elementary stochastic exchange model, the comparison between, say, the analog of the linear statistics, that is the behavior of a single random walk on a graph, and the behavior of the whole stochastic exchange model are difficult to compare in general. And it just comes a number of open problems. It would be even nice just to know if there are instances that answer affirmatively to these questions. All right, but I promised a talk about mean field models, and I promised to stick to the models that Federico introduced. So let me call U now a beta random variable. Here everything will be symmetric, so the parameters alpha do not depend on the specific vertex or particle as you wish, just some alpha, you pick some alpha, and you take a random variable U that is distributed as a beta, symmetric beta random variable. You have your complete graph with set of n particles. You have your initial energy profile with total energy equal to 1. And then you perform the same actions that I used for the averaging process, with the only difference that now instead of averaging, we do KMP. So when two particles X and Y are selected for an update, then what you do, well, you split the energies of the two particles accordingly to the random variable U that you sampled, and you exchange one of these two parts according to the KMP rule. That I remember, I recall it's essentially confined in this representation here by a 2x2 matrix. So after the updates, the first particle will have a fraction of the total energy that it's proportional to U, while the second particle will have a fraction of the total energy, which is proportional to 1 minus U. And then Federico introduced the hidden parameter model associated to this KMP. So if you want to see it more directly, what does this model do? Well, you have these two energies sitting at site X and site Y. Still, you split the energies according to this U random variable, but this time, instead of changing the top part, the particle X will discard a fraction 1 minus U of its initial energy, and the particle Y will discard a fraction U of its initial energy, like this, and the remaining parts will be copied on top of the other particle, like this. So after this sort of update, of course, the two particles equalize, so they will have the same energy, but the system is not conservative. So Federico used the same matrix and row and column vector. I would rather prefer to reverse the matrix. So the matrix which is associated to this HPM model, to me, is just the adjoint, is the transpose of the matrix associated to the KMP. So as you see, this is not row stochastic anymore. And finally, there is another model that I would like to consider. That is what I will call the beta averaging process. How does it work? Again, you split the energies at the two sites. This time, each particle retains a fraction U of its initial energy and exchange the fraction 1 minus U. So you don't have equalization in this case, but still you have a stochastic exchange model in the sense that the total energy is preserved by this dynamics. And in fact, the associated 2x2 representation of this model is given by this stochastic matrix, which is symmetric. So in a sense, the hidden parameter model of this beta averaging is itself. You cannot transpose it. You can transpose it, you get the same model. Well, let me do just a couple of remarks about these three models. Well, they are pretty different. I will discuss more the differences in the next slide. But if you look at the marginals of these three matrices entry-wise, well, they are the same in each entry and for any of the three models, just because of the symmetry of the beta random variable. So U and 1 minus U have the same margin. And the second comment is that if you take the limit as alpha goes to infinity, as anticipated by Federico, at least formally, you recover the fair averaging a la Bourgain that I introduced at the beginning of this talk, because then U converges to a Dirac distribution on 1/2, and then these three matrices are just 1/2, 1/2, 1/2, 1/2 in any of the three models. All right. Nevertheless, for the rest of the talk, I won't need to assume U to be beta distributed. I will make a sort of generalization. I will consider U to be any random variable in 0, 1. We'll just ask it to be symmetric, so that the observation about the marginals continues to hold true. And non-degenerate simply means that it's not a Bernoulli random variable. Okay, it's not just half probability 0 and half probability 1. It's something less degenerate than that. And then I will consider the three models presented in the previous slides, but with this general assumption on U. So in order to avoid to introduce any further vocabulary, I will just call KMP like the models of the form 1 U, 1 minus U, U, 1 minus U, HPM like the transpose, and averaging like the symmetric version. So now the claim that I'll try to defend for the rest of the talk is that despite these models looks pretty different in terms of their steady state behavior, for example, once the distribution of U is prescribed, all of these three models exhibit the same mixing behavior. So in a sense, the mixing behavior of these three models, despite they may look different, is universal and is related only to the choice of this update random variable U. Doesn't matter whether you look at KMP, HPM, or averaging like models. So let me try to explain first the differences between the models. So for what concerns the KMP-like, we already observed this is a conservative model, so the energy is preserved. Moreover, even when U is not a beta distribution, well, you can still work out some contraction argument showing that there is a unique stationary distribution as soon as you prescribe the initial total energy. Okay, so you give me an initial profile. I don't care which is the initial profile. I just care about which is the total amount of energy in this initial profile, because regardless of the specific, I will always converge to the same steady state. And moreover, thanks to the symmetries of this model, of course, this stationary distribution must enjoy some exchangeability property. Of course, there is no reason for which the first and the second coordinate should have different marginals. While, as observed already by Federico, these HPM-like models are non-conservative because the associated matrix here is non-stochastic. Nevertheless, they satisfy some maximum principle in the sense that if I look at the particle having the maximal energy in the initial configuration, well, then as soon as the process runs, I won't have any particle having a larger energy along the process. This is almost immediate if you take 2 seconds to think about it. And as Federico already pointed out, the law of this HPM, the stationary law of these HPM-like models will be supported on flat configurations. So these are the only possible stable configurations. Nevertheless, here, the law of the stationary law does not depend only on the initial amount of energy, but it actually depends on the specific choice of the initial configuration. So you see, okay, already these two models are quite different. For what concerns the averaging-like model, this is of course conservative, and like this explains the name averaging-like. Like the first model I presented in this talk, it has a very degenerate equilibrium distribution because eta infinity will almost surely be 1 by n everywhere. So the stationary distribution is a Dirac mass in the center of the simplex, regardless of the initial configuration. Okay, just depending on the fact that I will always stick to have initial configurations in which the total amount of energy is 1, regardless of these three models. All right, so let me also point out that none of these three models is reversible in general. For arbitrary U, you don't have any explicit expression for the law of the stationary distribution, so they're very different at equilibrium. But I keep claiming that if you study the convergence to equilibrium in a proper way, they actually look all the same. Well, but what's the proper way to quantify distance to equilibrium? Well, the first natural attempt is to consider the total variation distance. So you just take the total variation distance between the law of the configuration at time t and the steady state. Well, in the variational characterization of the total variation distance, this is simply a half of the expected probability that two configurations differ when those configurations are sampled according to a coupling having marginal eta t, having marginal the law of eta t and the law of eta infinity, and you take the infimum over all the possible couplings. Nevertheless, if you if you believe this universality picture that I keep claiming, well, this cannot be the right notion of distance to use. Because in fact, for AVG and HPM-like models in which the configuration at equilibrium is singular, must be flat, well, then it's clear that there is no chance that these models in general converge to equilibrium in this strong total variation stance as time goes to infinity. So the distance to equilibrium will always be 1. Because at the equilibrium, they're exactly flat. So as soon as there is even a tiny point at which the energy is slightly different than flat, then you can perfectly distinguish the configuration of time t from that at equilibrium. So this notion is too strong. But to understand which should be the right notion, let's think about what we have done for the classical averaging process. Well, there we consider the expected empirical L1 distance. And if you think about it for a moment, then you realize that in the case of the averaging process with unitary total energy, well, this is just a rewriting of what it's maybe more elegant to look at as Wasserstein-1 distance. So you simply have to lift the L1 distance on the simplex to a distance in the space of probability distributions on the simplex using the classical Wasserstein approach. So in the specific case of the averaging, this Xi prime is sampled according to the equilibrium distribution, but the equilibrium distribution is the Dirac at a point. So there is actually no coupling here. So there is only a trivial coupling in a sense. And therefore, this expression here reduces to the one in the green box. But for the other three models, while this notion here of distance to equilibrium is not meaningful because it at t won't converges to the center of the simplex in general, well, this notion of equilibrium here, of distance to equilibrium here, might instead make sense. Well, actually, at this point, those of you having a background in physics maybe could argue that, well, when you consider this mean field system, well, what you can typically expect to observe about the system is not the exact energy profile. So you don't know this particle labeled 1 as this energy, particle labeled 2 as this energy, but you rather just measure, in a sense, the density of particle having a certain energy, say. So you are actually interested in the unlabeled particle system. And therefore, if you adopt this perspective, then this W1 distance is maybe too strong, and you might rather be interested in this calligraphic W, in which you simply forget about the labels. Or if you wish, you don't compare two configurations based on the L1 distance, but you first move from the space of configuration to the space of the order statistics of the configuration, then you just compare the order statistics. So this just amounts to take an extra infimum here over all the possible permutation of the labels, and then take the Wasserstein, the infimum over the couplings. So this here is, of course, a weaker alternative, analytically speaking, just because there is an infimum inside the expectation, so it's weaker than this, but also because you're simply saying that you cannot use the particle labels to distinguish between configurations. And then one realized that there is this chain of inequality, so that the W, calligraphic W, is weaker than the normal W, and this in turn is weaker than twice the total variation distance. Let me point out that actually for AVG and HPM-like models, this calligraphic W is exactly the same as the normal W, because at equilibrium, the configuration will be flat, and therefore there is no reason to run this infimum over the configurations, and this is completely ineffective, right? Because this Xi prime will have all the entries being the same. But in principle, for a KMP-like model, so for a proper stochastic exchange model, non-degenerate, well, these three inequalities are not sharp in general. They are not identities in general. Okay, so we identify now two possible notions of measure that might be of use in computing convergence to equilibrium. Just a couple of sanity checks to see that these are actually amenable, useful for this kind of analysis. Well, first of all, it's possible to show that these distances for a prescribed initial configuration are not increasing in time. And this is something you really want from if you want to analyze convergence to equilibrium. And the second observation is that by linearity of these models and using some convexity, you can actually realize that if you stick on initial configuration which are in the simplex, then the worst case ones are those that charges all the energy at the beginning at a single particle. This is true for the normal W, but also for the calligraphic one. So for this reason, in the spirit of the classical Markov chain analysis, I will stick to the worst case analysis. And therefore, every time I consider a W distance, I will simply forget about the initial configuration and always assume that the initial configuration charges all the energy at a single particle, both for the normal W and the calligraphic W. All right, so we are almost in shape to go to the main result, which I present in this talk. Just a couple of further quantity to introduce. So consider any of these three models and consider any update rule as soon as it's symmetric and non-degenerate. And let me call U hat the size bias version of U. It is simply a random variable having this size bias CDF. So let me point out that these two here in front comes from the fact that U is symmetric in 0, 1, and therefore the expectation of U is 1/2. And when you divide by the expectation of U, you get these two in front. And then let me call H the expected logarithm of U hat up to a signs change, just to ensure this is a positive quantity. And S square, the variance of the log of U hat. And moreover, it will be convenient also to denote by R the ratio between standard deviation and expectation of the log of U hat. And then with this notation at end, let me call entropic time, or Tnt. Well, it's a quantity of the order of n log n, where n is the number of particles in your system, with a specific constant at the denominator that is just twice h. And I will call the window, we'll see where I'm getting to, Tw. Well, it's a quantity that depends on r and h, and it's of order of n square root log n. So it might be comforting at this point to realize that in the specific case in which u is the Dirac at 1/2, well, this Tn is just the T star in the result by Chatterjee and co-authors, and this Tw is exactly the same Tw in their paper. In fact, the variance of log of U hat will be 0 in that case because the U doesn't fluctuate. And so this is 0, and you recover exactly the same quantities. And then the result is essentially what you would expect, that regardless of the three models, if you study this W distance at a time that is of the form entropic time plus beta times the window, well, in the thermodynamic limit, this will converge to twice Gaussian tail. Gaussian tail that this time is not just evaluated at beta, it's evaluated some beta transformed by this means of this green quantity R. I will discuss it in a minute. But so this is in a sense the natural generalization of the answer to the Bourgain question, but to this more general setup. So we have a cutoff occurring at this time here with an explicit window and an explicit Gaussian profile, regardless of the specific model. So it could be that you are looking at an averaging-like process or a KMP-like or a HPM-like. The stationary state looks very different, but if you measure how distant they are from the stationarity at time of this form, then you will always get the same quantity. And let me point out that if you replace the normal W by the calligraphic W, you get the very same result. So it's the labeling of the particles doesn't really matter. All right, so just a brief comment on the special case in which U is a beta random variable. Well, in that case, you can compute explicitly the quantities H and S squared, just an integral with respect to a beta density. As you can imagine, will appear some gamma, the gamma function, etc. It's not really interesting knowing the explicit expression of these two quantities. Just let's look at the plot of the quantity H and S squared as a function of alpha. Well, they both start at 0, and then as alpha goes to infinity, the blue line will eventually asymptotically reach log of 2, while this S squared will eventually go to 0. So as alpha goes to infinity, we don't recover the Chatterjee encoders result just in a formal way, but actually in a quantitative way. Namely, if you give me a large value of alpha, say alpha equal to 100, then I can compare the mixing time in this Wasserstein sense of the, say, KMP-like model with that choice of alpha, with that of the original averaging process, and look how much they differ. Moreover, for KMP-like models, this W1, we said that it's smaller than twice the total variation distance, and therefore, since in the KMP setup, the total variation distance is still a meaningful way to quantify convergence to equilibrium, as an immediate byproduct of our result, you get some lower bounds on the total variation mixing times. For instance, in the special case in which alpha is equal to 1, like in the original paper by Kipnis, Marchioro, and Presutti, then the problem of computing the total variation mixing time for this KMP model in discrete time on the mean field setup has been already addressed 10 years ago by Aaron Smith, who proved a pre-cutoff result, which is something a bit weaker than cutoff. I don't want to enter the details, but on the very same time scale. So it showed that convergence to equilibrium in the total variation sense occurs on scales n log n, as for our weaker W metric. So it left open the question whether it might be the case that W1 and total variation distance actually behave exactly in the same way. So they both have cut off at the same point. This is not known, but this is a nice open problem. All right, so now let me just say a few words about the motivation underlying this name, entropic time. Well, the first motivation is just naive. So this quantity H here appearing on the entropic time is up to a sign change, the expectation of the log of the size bias version of U, that more explicitly can be written this way, in this entropy looking fashion. So it's just the expectation of U log U up to multiplying it by -2. And from this expression is immediate that this quantity is smaller or equal than log 2, regardless of the choice of U. And this, in a sense, tells us that the classical averaging process discussed in the first slide is somehow the fastest mixing among this whole class of Markov chain. Recall that this H is in the denominator of the entropic time. So the smaller it is, the longer it takes to converge to equilibrium. And this equals log 2 exactly in the result by Chatterjee encoders. And the second motivation underlying this name is more functional analytic. So you might consider the averaging-like model, general U, and look at the expected relative entropy between the configuration at time t and the flat configuration. Then adapting the argument in a recent paper by Bristella and Caputo, then you can show that for any initial configuration eta 0 in the simplex, then the expected relative entropy decays at a rate that is prescribed by the entropic time. And actually, this quantity here, Tn, is the smallest constant you can plug here to have this inequality all true for every time and for every initial condition. So, in a sense, this is some sort of analog of a modified log-Sobolev constant for the averaging process. And the third and last motivation is more of phenomenological nature. I won't have time to enter the details and just give you the idea. So if you look at the proof of our result, you would realize that the way in which the process goes toward equilibrium is by somehow accumulating some tiny random progresses. Okay, and it's the accumulation of these tiny random progresses that eventually lead the process toward its steady state. And what makes the cutoff emerge is like some sort of concentration phenomenon for the accumulation of these tiny random progresses, pretty much in the spirit of the naive parallel I gave you at the beginning. So this high-level perspective can be used to frame our result in the entropic time picture, which is an high-level perspective to deal with several models of Markov chain exhibiting cutoff, and which somehow underlying the analysis of several papers appeared in the last decade, just two authors among those who contributed to provide this picture. So I won't comment anymore on this. This is just a comment more of phenomenological nature, maybe meaningful only for the expert in the audience. So what I'll try to do in the next 5 minutes, okay? So let me just, so I keep claiming that despite these models are different, well, we saw that there is some sort of universality in the way in which they approach equilibrium. And this universality is related to the fact that there is a key similarity underlying these models. But if you want to appreciate this similarity, well, what you have to do is actually to lift the whole process on a larger state space. You need to consider a richer process, which are called the pile dynamics, such that the original stochastic exchange model can be obtained just by projecting somehow this richer process. And as soon as you take this lifting, you can prove some identity which it's completely insensible to the choice of the model you make. It's only sensible to the choice of the update random variable u. And in some sense, the convergence to equilibrium is actually governed by this identity. And this is somehow the reason underlying the universality behavior for the Wasserstein-1 convergence to equilibrium in these 3 models. So let me describe briefly what this pile dynamics is about. So you do your process. Now the picture here is for the KMP, but you can do the same picture for any of the other 2 processes. So the process goes exactly as described before, with the only difference that now I color the fraction of mass that are exchanged. So every piece of mass comes with a color. And when I exchange mass, I continue to keep track of the colors. So for example, if here there is an update as these 2 particles, then I use the same random variable u to select the top part of the first, what I will call piles. So now the energy is organized in piles. So here I have 2 piles. I use the same u to cut the pink and the green one. And I use the same u also to cut here the blue and the yellow one. And then I exchange the top part of each pile. Of course, if you forget about the colors, this is exactly the same KMP model described before. But now the main idea is the following. If you continue to keep track of these colored piles, and you fix some threshold theta in 0, 1, So theta, you have to imagine it as sides. Then you may consider a subconfiguration of energies, which is obtained by retaining only the piles which have a size that is larger or equal than theta. Like here in this example, at this time, I only have 3 piles that are of size larger than theta, this, and this. So I discard the others. Let me call now capital T of t, independent binomial random variable of parameters t and 2 by n. And here comes the identity. So if you are interested in the expected quantity of energy that is contained in piles that have size larger or equal than theta, well, this expectation here can be written as an identity as the probability that the sum of IIT random variable distributed as the log of my size bias distribution falls, or this sum falls within some threshold that depends on the choice of theta. One has to keep in mind that there is here, we have a sum of IIT random variables, but actually also this number here is random, so also the number of sum answers. So I don't have time to prove this identity in full details. It actually is a single slide, but I'm already running over time. Just let me make 2 observations to try to convince you. Well, the first thing to observe is that when a pile is involved in an update, then these piles gets erased out of the system somehow, and it produces 2 new piles, regardless of which of the 3 models you are considering. Of course, if the model you are considering is a conservative one, then the size of the 2 newborn piles adapt to the size of the pile of their ancestor. If you are considering an HPM-like model, which is not conservative, okay, this won't be the case, but still from a single pile, at an update, you get 2 new piles. And the second observation is that regardless of the 3 models, if you focus only, so if you know that some pile at time t has been updated s times, well, its size is distributed as the product of IIT random variable with low u. And this is just because the random variable u are symmetric, and the marginals of my 2 by 2 matrices are all the same, regardless of the model. So these 2 observations, it's, somehow the underlying idea for this identity, which is insensible to the specific of the model. Now, once you have this pile identity in mind, then, the heuristic argument for the proof of the main theory is the following. You take a time that is of the form Tn plus beta Tw, you take some theta that is, say, of order 1 by n, up to some subpolynomial correction, and you realize that for this choice of t and theta, well, this quantity here on the left-hand side of the probability has an expectation that is equal to the quantity on the right-hand side. So you're really on the border of you're really on the mean. So this is exactly the mean. So this probability, you cannot decide it, you cannot say what's the value of this probability if you don't look at the second order. So you're really on the fluctuation regime of this sum of random variables. So you need to prove some CLT resolve for this sum of random variable in the classical way, and to deduce that this expectation is exactly of a Gaussian tail in the limit for this specific choice of t and theta. So just let me point out that since you are adding random variable and a random number of random variables, then you have to take care of both the fluctuation of the summands and the fluctuation of the number of the summands. And this is why here you get beta, but also this factor R that takes into account the fluctuation of these guys. While in the case of the Burgen problem, well, this is always log 2. So the only fluctuation that you have are the fluctuation of the binomial, and this is why you don't get this factor, you just get it. And then at this point, you can imagine that the rest of the work is just to prove that actually the fastest time one distance at time t is at first order given by this expectation. So what contributes to the distance to equilibrium is just the quantity of mass that is organized in piles that have sides much larger than 1 by n. So I don't have time to go through the proof, but you see just 5 equalities, not more than that, and not even about sketch of upper and lower bound. So let me just arrive to the conclusions. I hope to have convinced you that by exploiting this pile dynamics, one can really get a complete picture of the convergence to equilibrium, at least in this Wasserstein sense, of a very broad class of mean field exchange models, averaging models, or the hidden parameter models. And when I say complete picture, it's not just because we have a precise result, it's also because we can really understand which is the physical mechanism underlying the convergence to equilibrium, and you can relate it to this simply to a law of large number and to a CLT, like in the naive parallel I made at the beginning. Of course, this is only tailored for mean field system, and as soon as you enter some geometry, everything remains open, even for the simplest case of the averaging process a la Bourget. Well, beyond Wasserstein 1, there are still some open problems. Well, there are many open problems, actually. If you want, for example, to study the total variation mixing of K and P-like models, here is just a few results that have already been mentioned during my talk and the one by Federico that address the problem on specific setup, like mean field or one-dimensional. And, well, another interesting question is about the speed of convergence of the associated discrete duals. What do I mean by this? So take the generator of your K and P-like model, but constrain it to act only on polynomials of degree K. This can be read via the analysis that Federico presented as the generator of a K-particle system evolving on your graph. Could be even mean field. And then this problem frames really nicely in the setup of in finite state Markov chain. So you may want to characterize the convergence to equilibrium in total variation, but there are no many results for the moment beyond the one mentioned here. So I think my time already expired. So just let me thank you once again for your attention.
Thank you very much, Matteo, for the nice talk. And as before, other questions, just please raise your hand or unmute yourself and ask. So let me start with one. Indeed, so in Federico's talk, the law of this random variable u was depending on the vertices, right? On the pair of vertices. Well, here you choose the same law for everyone.
Yeah.
But I can easily imagine that this is a mean field problem, and if you kind of decide to take a sort of I don't know, maybe take the parameters of your beta that depends on vertices and just make the model a bit inhomogeneous. I would expect that you get a sort of similar result, but probably it's a matter of understanding this pile identity, right? That might be hard.
Yeah, okay, yes. So you lose somehow the symmetry that is underlying this pile identity, but it might still be the case then some sort of result goes through, and I would be positive, but fairly positive. Yeah. I never tried, and we never attempted to do this, but of course, everything I said, it's very, very tailored to this mean field, completely symmetric setup. So we try to generalize in terms of the exchange model you consider, but we keep this symmetry intact in order to
so the symmetry of the law of the distribution.
Yes, yes. The U is the same for every vertex, for every couple of vertices, and everything is indistinguishable in terms of particles.
Okay.
Which is, I mean, it's somehow natural if you think in terms of kinetic theory. So it's one would expect.
Yeah, but okay, it's also maybe natural if you just think of making something slightly inhomogeneous in a sense that you have a positive proportion of vertices with some characteristic, and with some other probably it will work as well. Yeah,
might be.
Yeah, thank you. Are there other questions? Yes, please, Andrei, just unmute yourself.
So, question is, could this be put in any other topology? You mentioned here the questions open to geometry, and would the choice of the distance you have W1 and the total variation then make sense? And would it make sense how to analyze it? There are probably many open questions, but yes, thanks.
Okay, yes, thank you for the question. And indeed, yes. So this W1, the normal one, I think it still will still make sense to be analyzed, because in fact, when you study the averaging process, we actually study this W1 regardless of the geometry. But for what concerns the calligraphic W1, which of course it's the same distance if you stick to averaging and HPM-like models, but if you go to KPM-like models, KMP-like models, that these are the most natural exchange models that are conservative, etc. Well, then this normal W and the calligraphic W are not the same. And if you're not in the mean field setup, then the calligraphic W is not easily shown to be monotone anymore. So we don't have an easy proof. We don't have a proof actually for the monotonicity of this calligraphic W. So in that sense, of course, when you have geometry, somehow you want to use the labels of the vertices. So I don't know whether this answers your question, but that distance is not good.
Thanks.
Okay, good. Let's see if there are other questions. So, but let me just ask something else. Going back to the symmetry of the distribution U, what do you expect if this is not true? So if
well, I mean, I would expect that the same sort of result should go through if you take symmetry in a weaker sense. For example, if you consider the immediate exchange model that Federico presented. So you have U and V, so two different random variables, but U and V have the same law. So you have U, 1 minus U, 1 minus V, V, but still you have, so these are still symmetric, and therefore you still have the same marginals in the four entries of the matrices.
Yes.
So, okay, there is some technical point that, I mean, you cannot see from this talk, it's hidden in the paper, but in which somehow we use explicitly the fact that, so it's not of this, I mean, the immediate exchange model is not part of the models we are studying, but I would expect that this can be fixed and actually, okay, it's still a symmetric model in a sense, but it added some level of generality because you may have different two random variables involved in each update.
Yeah. Okay, but the idea is somehow always that you are going closer and closer to the equilibrium via these small steps as well.
Yeah. This I think it's pretty general.
Yeah.
And this is what you see from this law of large numbers. So the improvement steps are exactly this adding up this logarithm of U hat. So you can really give a sense to it in this way.
Yeah. And is it true? No, maybe this is just it looks like that, but it's not true, because it looks like then that it depends on how many improvements you're doing. So that's the law of this T, capital T, that you had, but that those are all the same size. But this is probably just a fact that you can write it like that. It's not true. So initially, probably the improvements are larger. Are they?
No. It's always the same. I mean, this is just an high-level perspective. It's nothing analytical, but you are just adding IID random variables. So they are all the same in terms of, okay, at the beginning, of course, you have a big pile, then you split it and you have two big piles. Still, you are extremely far from equilibrium.
Yeah, but you're saying...
So that's point. So So you start accumulating this, but just when the piles are really of the order of 1 over n, then you are at equilibrium. And this, of course, in a concentrated way, just because of the law of large number. That's
I see. Yeah. No, that's a very nice analogy as well, also to give the idea of what's happening. Yeah. Thank you very much. Let's see if there is still some other question. Otherwise, let's thank both of the speakers again. And of course, maybe we will leave the Zoom open for a while. So if someone wants to ask more, but thank you for your nice talks.